All right, good morning everyone. So remember that we had started talking about the so-called open loop testing based or receipt based design. So the main idea was to excite the system with a step input after bringing the system into around its operating point. Okay, because most of the systems might be nonlinear or may have non-zero initial conditions, right? The way we treat these systems is that we bring them around their operating point, and then we apply essentially a step input, and we observe the behavior around the operating point, assuming that any controller that we would design would be also operating around this nominal or operating point. Okay, so we apply a step input to the system around the operating point. We observe the response. Obviously, you can, if you observe this, the response to be linear, you can try to fit a linear model to it. But we also discussed that we have a new tool, which is the first order plus dead time model, which is a first order model supplemented by a time delay, okay, a pure time delay. And we can obviously also extend this into a second order model as well, although we haven't focused on that. There is also something called the second order plus dead time type of a model, okay? The rationale behind it is that many higher order systems, and we will see this in the subsequent lecture, is that even higher order linear systems can actually be approximated by lower order systems plus a time delay. Okay, so we have also learned this nonlinear model, right, which is the first order plus dead time model. Well, it's not entirely actually nonlinear. It's still a linear model, but we will see that it is something called infinite dimensional. Okay, the reason being, in fact, finite dimensional linear models that we have, you know that they are actually, they have rational transfer functions with a polynomial of finite order in the numerator and a polynomial of finite order in the denominator. But the time delay model that we introduced actually has an exponential function in the numerator. An exponential function, unfortunately, cannot be represented exactly by a finite polynomial. It can be represented by its Taylor series expansion with infinite number of terms. That is why time delay is often characterized as an infinite dimensional linear system. Okay? So what we have done is that we discussed this new model, the first order plus dead time model, and then based on this model we introduced certain design formulas for the PID controller. We haven't derived yet these formulas, and their derivation requires a bit more understanding of the time delay. Okay, in fact, the first two lines, the PID, the PI and some of these formulas actually don't require it, but at least the last two rows requires a better understanding of the time delay and its approximations that we will spend some time on today. Okay. By the end of today, I hope we will be at a point to start discussing how we can derive these formulas. Okay, so but for the time being, we basically, once these design formulas are available, okay, and I have forgotten the design formulas for the P controller, and I'm going to give it right now. But essentially, the procedure of designing a PID controller, the so-called receipt-based method, is composed of bringing the system around its operating point, applying a step input, In the industry, there is a jargon that calls it a bump test. Bump test meaning apply a step input, record the response, and to that response, you fit a first order plus dead time model. And once you have the model parameters, which are the process gain, the process time constant, and the process time delay, right? These are Kp, tau p, and theta p. These design formulas actually give you a controller based on those three parameters. Okay, so you can just plug those values into the design formulas, and you obtain a starting point for a reasonable PID or PI controller. Okay, there was one more parameter as part of this design that is not part of the plant model, is actually what is called a tau c. Okay, the final parameter over c, which is tau c, and tau c is actually also a design parameter, and in fact it specifies what is your desired response look like. Okay, tau c is the time constant of an approximately first order response of the controlled closed loop system. You make a choice for tau c, and you use the plant parameters in order to come up with a controller that's going to behave in a way that will generate this desired time constant. Okay, and please note that the design, the objective of the design of a controller can be twofold. A controller may be designed in order to stabilize the system, meaning that improve the stability of the system, okay? Or it may be designed in order to somehow make the system faster, okay? For example, in a heating system, actually the plant time constant may be very low, and the design of the controller may be to accelerate the heating of the plant, okay? But on the other hand, for some systems that are closed or already unstable, you may be designing a controller in order to slow down the system to make it stable. That's why we have these three different ways this tau c can be assigned. Okay. For example, in the case of aggressive performance, right, you see that the closed loop system actually is much faster than the open loop system, because the desired time constant is set to be 1/10 of the time constant of the plant. Okay, but in the conservative case, it can also be the case that the closed loop time constant is actually 10 times slower than the plant time constant. This means you are actually trying to slow down the system, most likely in order to make it more stable. Okay. We also discussed something called the controller output filter. Okay, because if you remember, we had discussed the fact that a derivative often amplifies the high frequency noise in the signals that are being differentiated. In this case, the error signal. Okay, so if a high frequency component is present in the output of the controller, that will drive the final control element or the actuator with a high frequency signal that's going to result in some kind of a jitter. So this filter is designed in a way that's going to suppress that high frequency components and therefore prevent the actuator of executing very fast jitter-like motions, because that's going to have some negative effect on the performance and health of whatever hardware is involved. Okay. Let me also, as a final note here, let me also write down the design formulas for the P controller. Okay. So let me, so hold on a second. So design formulas for the P controller which was not given in the table. These are based on what is called the integral of time-weighted absolute error. Okay, so these are so-called EE formulas. They are based on minimizing the integral of the error. Okay, integral of time-weighted absolute error. Okay, so they just specify a P controller. That means they just specify a simple gain for the controller. So for the moderate response, we have Kc, the controller gain given by 0.2 over Kp, and tau p over theta p to the power 1.22. Okay, and if you want a faster, more aggressive response, okay, we have Kc prime. Okay, so 2.5 Kc. So you basically increase the gain by 2.5 fold in order to obtain a more aggressive response. Okay, so these are your kind of two additional design formulas for the P controller. Okay. There is also something, just to give you kind of a at least you know the name. Okay, there are a set of older design formulas which have worse performance. These are called, hold on, design formulas. These are called Cohen-Kuhn design formulas. I will not give them, but just you know the name. Okay, if you hear something called Cohen-Kuhn design formulas, these are formulas from 1953. We will in fact discuss the derivation of these so-called IMC based design formulas. Okay, newer design formulas. Okay, so these have been developed around 1989. Okay, those are the ones that we will discuss their derivation based on something called a direct design and internal model control based design. So these are much more recent than Cohen-Kuhn design formulas. Okay. All right. Do you guys have any questions? Now, let me also give you kind of an outline of my following, the follow-up of the lecture. Okay. So where do we go from here? Well, we will basically further analyze the so-called dead time or time delay, including why it's actually is why it's so popular and so on and so forth. Okay, so we will kind of also discuss effects on system stability and behavior. We will discuss linear models, linear approximations. Well, let me not say linear because the time delay is also linear, but let's say finite dimensional approximations to the time delay. In particular, we will discuss something called Pade approximation. And then we will apply applications or in PID controller design. Specifically, we will discuss something called direct design, which will, which will very briefly use an approximation to the time delay. But further on, we will discuss something called internal model control. Internal model control. So these two actually will give us derivations of design formulas. Okay, so we will know exactly where those design formulas are coming from. Okay, we will start with direct design, which will cover some of the design formulas, and then IMC will be kind of a more elaborate discussion, and that's going to give us the full PID design formula that is on the last row, the last two rows of the design table. Okay. Any questions so far?